project is a study of the Kingfisher's beak aerodynamics, which I made as a biomimicry project for my biology class. So biomimicry is where humans use solutions from nature to help solve design problems. So in this case, the Kingfisher's beak was used as a model for the Shinkansen 500 series bullet train. So this program is split into 5 tabs. So in this first tab, we first look at a Kingfisher's beak profile, and we plot points along the upper ridge. So I already did that here, but there's tools here to help you zoom in and plot these points. So once those points are plotted, we can send this to the second tab. So here, the program will map those points to a mathematical curve. So here we can choose a model. We'll use a third-degree polynomial. And here we can see the points of the beak that we just mapped. And what this does is this will map a curve to it, which is a degree 3 polynomial. And it will give us R squared and RMSE measures, which measure how predictable the points are and the error of each point, which just helps us see the profile of the beak more clearly in a mathematical way. So then we can go to the third tab. So in the third tab, we're able to modify the fitted shape that we made using these 3 parameters: the tip sharpness, camber, and taper rate. So as these values change, the program will automatically estimate the drag coefficient, or the CD right here. So we can move the sharpness, and as you can see, our fitted line that we made in the previous tab will adjust based on the adjustments we make to the different parameters here. And we also have a automatic optimizer here. What this optimizer will do is it will show us the most optimized drag coefficient that we can make realistically within the boundaries of physics. So after running the optimizer, we can go to the fourth tab. Here, we can draw a comparison with the Shinkansen 500 series train and the Kingfisher beak, as well as the optimized shape that we made in the last tab. So here we can see exactly how the Kingfisher beak profile impacted the Shinkansen series train. And we can also see how our modified shape performs versus the train. So in this case, our modified shape has a 22% lower drag coefficient than the actual train itself. But obviously the train is not made just for the lowest drag coefficient. The train was made for like low tunnel boom and different factors like that. So in the final tab, we can generate a report on all of the other tabs that we use to collect data. So the main problem that this project solves is that it turns a biological shape into something that can be studied and compared to an actual engineering design. And what I learned from this project is that small decisions like how points are traced at the beginning can actually strongly affect the final result. That's why I spent so much time on this first tab, making sure that the user was able to fit the shape as well as possible, because that would allow the rest of the project to run smoothly. Thank you.